Welcome to the first education series presentation from the Laboratory for Advancing Rock Engineering Knowledge, the University of British Columbia, Vancouver, Canada. My name is Davide Elmo, and I'm a professor of rock engineering at the MBK Institute of Mining Engineering at UBC. And this presentation is about rock bridges. You see the title, it's a combination of engineering, but also philosophy and quantum mechanics. We're not going to do the mathematics, don't worry about that. But we're going to see how the interpretation of rock bridges, what we call the Bologna Interpretation of rock bridges, blend with the quantum mechanics philosophy. First of all, I also would like to acknowledge the contribution of many of the people that actually helped me throughout my career when it comes to researching rock bridges, primarily Professor Doug Stead from Simon Fraser University, my current PhD student, Beverly Young, Zarin Tasmin, that she worked with me as an undergrad student last year, and Professor Borgatti from the University of Bologna in Italy, Dr. Gianluca Marcato, and Dr. Stavio Donati from University of Bologna, and Gianluca Marcato from Siena and Padova. So what are rock bridges? This is actually the question we're going to try to address in this presentation. And I worked on rock bridges for the last 17 years. So it's a long quest for me to try to understand what is a rock bridge. And there are many questions, and many of these are actually still unanswered. For example, what evidence do we have of rock bridges? Well, we know they exist. And you can look at the photo here, you can see that you have a situation where a block is standing on a slope and the block is not moving. So what is actually holding the block in place? So, assuming that we can actually define what is a rock bridge, what are the parameters that define rock bridge strength? And how do we then incorporate rock bridge strength in analysis? And most of all, how do you actually define rock bridges? We see actually from this photo again, you don't see them. You can't really touch them. You don't see them. They don't really exist per se. They exist, but they're not reality. That's what we're going to see in this presentation. And this is the complexity that we have to address in a way to basically really understanding the role of rock bridges in stability analysis. And also there's another question, which is we're going to see if rock bridge is indeed related to the process of cracking, fracturing, so rock mass damage. How do we incorporate this mechanism in a simulation that only works with continuum analysis? And this is where the rock bridge definition, the Bologna interpretation, comes from. This is where rock engineering meets quantum mechanics. The great physicist and Nobel laureate Niels Bohr once said, "Everything we call real is made of something that cannot be regarded as real." This really what is a rock bridge. It's something that we know exists, but you cannot really call it real. Another great physicist, Professor Jim Al-Khalili, we paraphrasing his sentence, and we can say a rock exposure is a curtain behind which there is no reality, only the potential reality. We see the rock face, but we don't know what's behind the rock face. We try to interpret it, we can do statistical analysis to look at the connectivity of the network, the fractures, but still you don't see it, you don't touch it as a reality. And this then links to, this is really where quantum mechanics philosophy and rock bridge study comes together. This is the definition that I gave a few years ago in a paper. There is no real geological feature to which you can point to and call a rock bridge until the rock bridge has failed. Again, you don't touch the rock bridge. And look at this photo here. This is two photos from the Barry Arch in Canada, one taken in 2002, one taken in 2020. You can see now, if you look at the 2020 photos, which blocks has failed. What are the failure surfaces? But you could not determine those failure surfaces in 2002. They were hidden behind actually other blocks. So your rock bridges were there, but you couldn't see them. So the definition that we can say is this one now. One cannot actually know where a rock bridge is until you measure it. And to measure it, you need a rock bridge to fail. So you can see that we actually hit in a paradox here. To measure the rock bridge, the rock mass needs to fail, which is something we don't want to do for design purposes. So how do you solve this big problem? We need a new paradigm for rock bridge analysis then. We need to change the way we think about rock bridges. Prior to failure, it's not a matter of describing rock bridges as physical deterministic entities. You cannot measure them as simply the connection between to intermittent joints. There are only potential rock bridges which exist everywhere at once. I know it sounds like difficult to accept that, but the fact that if you look at this rock mass here, the rock bridges are everywhere. You can't simply say the rock bridge is simply the connection between two of these joints. What are the loading direction? What are the strength of the joints? That also plays a part. It's not simply we shouldn't see rock bridges as a geometrical problem. If I do the simulation, I see where basically failure occurs. That's the rock bridges. But what you can see here now that it's a damage process. It's not as simple as one single crack connecting to joints. So only by looking at rock mass as it fails, we can summon the position of a rock bridge into existence, and therefore measure the rock bridge potential of the rock mass. It's a question of, we're going to see throughout the presentation, comparing before and after. You will have to do simulation, discrete element simulations with fracturing. Continuum analysis will not give you the right solution in this case. And if you look actually at the field evidence of this type of operation, this is work done by Shang et al. In 2017. They had a block, they managed basically to split the block open. The block was partially formed by discontinuity. Now you can see what is the discontinuity plane, what is the rock bridge. But see again that you have to break the block to see the rock bridge. You can't really measure it, the rock bridge, before the block has actually failed. And we have plenty of examples in nature. This is an overhanging slope. In Israel, you have what it looks like, if you look at the picture on the left, almost like a dangling tooth. This block that it's almost, you have to ask yourself, how is that possible, the block actually standing up? And it stands up because of rock bridges. You know they're there, but where they are, you don't know. And if you don't know where they are, how do you measure them? Because you can't see them, you can't really touch them. They're there at once, everywhere in the rock mass. This is actually another very good example from Italy. This is a tunnel in Italian Alps. You can see here from the photos on the left, there was this kind of block attached to one of the side tunnels. This block has been standing for many, many years. One day, we went back there to look at the tunnel, the block was on the floor. So what happened now to this block? Clearly, whatever rock bridge was there has failed. But this now has very clear implication, because you cannot say that the block, well, we can say the block was stable before, but you cannot say what was the factor of safety of the block. It was definitely stable, it became unstable, and it failed. So you can't simply back analyze before what is the rock bridge percentage. We can see now, if you look at basically the photo, what potentially was actually the portion of interrock holding the block in place. But you can't really see until the block has failed. Again, you can see now this paradox that you don't see them, you cannot measure them, because they only become real when the rock mass fail. And one more example. This is interesting, basically C-stack located in the Russian Federation. All this information comes from Google. You can see this monolith, in a way we can call it a monolith, 25 meters high roughly, only 1 meter and a half wide, very, very thin. Has been standing for hundreds of years, at least the record point that it's been there for at least since basically the end of the 19th century, so in 18th century. So it was definitely formed, it was part of the coastline. Why is it not failing? When you look at it, it looks like a very blocky rock mass. You can literally trace fractures from the top to the bottom. I mean, tracing doesn't mean that this fracture actually continues. They're definitely not continuous throughout. As those basically fractures be continuous, the block will simply falls apart. So there are rock bridges. But again, and rock bridges could be portion of interrock, means the joints are not fully continuous. It could actually be kind of cement, something that's cemented the jointed surfaces together. That's something also that we don't typically take into account in our analysis. Yes, we want to be conservative, but how do you explain now this structure standing? And if you look at the lab examples, again, you can see that once you take a block and then you make it fail, you can actually see now where the cracks occurred. And now you can call them rock bridges. But be careful when you look at this lab example. Look at the top row here. When you look at those, the fractures have been pre-inserted and they are open fractures. If I go back to this natural rock slope, the fractures are not open fractures. They are closed, very tight, potentially actually cemented. So what we're simulating here in the lab is something different from what you see in nature. What is also very interesting, actually looking at the bottom row of the simulation, you have the one in the middle where you have fully continuous joints and the failure occurs simply by sliding into the joints, and the one next to it on the left when the joints are still fully continuous, but failure occurs through basically breakage of the interrock. So again, this condition that we assume that a rock bridge is the distance between intermittent joints is not correct. You can actually have rock bridge failure in a rock mass with fully connected joints. It's a question of relationship between the connectivity of the network and the loading direction. And what about why we only basically look at rock bridges in terms of rock slopes? We are kind of fixated, everything is about rock slopes. But if you look at now this problem, these are pillars. Same rock mass quality, same jointing conditions, same interrock. If I change the loading direction with respect to the orientation of the fractures, I get a very different response. Either significant damage to the interrock or almost no damage to the interrock in sliding, like the one, this 50-40 model you see in the middle. So very different strength response. So how you define rock bridge strength when it's actually dependent on more than just the geometry of the fracture network? So you can see now that we have to kind of adopt a system that looks at the connectivity before and after. The relationship between the two is basically what controls the failure of the rock bridges. So now we have to basically deal with the actual difficult part, because when you look at the literature, when you look at the books, most of the analysis is done by looking at rock bridge percentage. So, and I also use this concept for many years until basically I started changing direction and seeing the problem with this concept. The problem with rock bridge percentage, as we say here, is that it treats the rock bridges as measurable deterministic entities. They are not measurable deterministic entities, we've seen. You don't see them, you don't touch them. And this goes back to the definition of rock bridge. You go back to Carl Terzaghi, the father of soil mechanics. 1962, he published a paper when he had this first basically evidence of this concept of rock bridges. Carl Terzaghi called them gap, but didn't call them basically rock bridges. And this idea of a percentage of rock bridge as the ratio between the total area of a fractures and the portion of that surface which are actually interrock. But Terzaghi made a very good comment already in 1962. He said the relationship expressed by this equation, the one here that defines the continuity of the fracture, is merely of theoretical interest because it's impracticable to determine the value of Ag. So what Carl Terzaghi was saying is that you cannot measure rock bridges. So you can't use measurement of percentage because yes, you can define them using this equation, but it's a merely theoretical exercise because the issue is then where are they and where you see them. And this is also in relation to the surface of a fracture. So I call them in-plane rock bridges. A few years later, Jennings developed a different concept of rock bridges, but he was looking at intermittent joints in the case of slopes. And now you can see we went from a three-dimensional to a two-dimensional aspect here. So basically you have a block that could be defined if those basically portion of interrock between the joints fail. And that basically gives rise to the concept of continuity given by this equation here, this K. So the ratio between the portion of the joints and the sum of the joints plus the portion of interrock between the joints. And Jennings developed some equation to basically account for this problem. So he said that you could substitute the joints and interrock with a material with equivalent properties. And here actually we can go off on a tangent, but like, are we dealing with a material with equivalent properties or an equivalent discontinuity? Because Jennings actually called it equivalent discontinuity. And it's different by simulating the problem as a material, with cohesion and friction of a material, and cohesion and friction of an equivalent joint. More importantly, when you look at the books, they always reference these two equations for equivalent cohesion and equivalent friction angle in relation to the continuity. 1 minus continuity is your rock bridge and becomes a rock bridge percentage. But if you look at the original paper by 1970, it's actually a different equation. So we also have to be careful which equation we use and how we use it. Because if I use the one that usually reported in every books, even the guidelines for large open pit design, you actually give more friction resistance to your problem. So it's actually less conservative compared to what Jennings was saying in 1970. But there's more limitation than that. And we're going to see now a problem. First of all, the concept of intermediate joints for coplanar joints. Joints are not always like that. Networks are more complicated than that. And it assumes that the rock bridge strength is spatially independent, which means it doesn't matter where the rock bridge here, you're going to get exactly the same behavior as long as you have the same percentage. Put the rock bridge at the top, put the rock bridge on the top of the crest, it doesn't matter, according to Jennings' equations. It's scale independent. We're going to see now a problem. If I have a rock bridge percentage of 5%, it doesn't matter if it's given by 5 small rock bridges or one just big one rock bridge. This is not correct because interrock strength is scale dependent. And more importantly, it assumes the rock bridges are measurable. It's this idea that rock bridge is just a geometrical entity. Look now the simple problem here. So you have a slope. In the first case, we have 2 joints separated by a rock bridge. And again, here we assume that that's where it's going to fail. So I'm assuming that, okay? I'm not saying that's the rock bridge. That's my assumption. That's where it's going to fail. The simulation is going to tell us whether my assumption is right or wrong. In scenario 2, we have 2 basically portion interrock separating the joints. Scenario 5 has 5 joints with 4 portion interrock. But if you think in terms of Jennings, in terms of continuity, and assume basically the length of the joints plus the length of the portion of interrock plus the other portion of the joint, divided by basically the amount of interrock that I have to break through, the percentage is always the same. It's always 5% in every single of this model. Now, what's going to happen now if I apply a foundation load on top? I want to see, will this kind of portion interrock fail at the same amount of force applied to the top of the slope? In the first case, the rock bridge, this gap in between the joints, fails at about 2.7 meganewton per meter. But when I have 2 separate rock bridges, separate gaps, the value of the foundation load that I have to apply is much smaller, 1.8 to 1.6 meganewton per meter. And you see the top, the first one on the top fails, then the one on the bottom fails. If I have 5, the value of the force I have to apply is much smaller, it's barely 1 meganewton per meter. So now you can see that it's the same problem from a percentage point of view, but it's very different the load that can actually be taken by the slope. So what it tells you that you cannot rely on rock bridge percentage. And here is the difficult questions for everyone now. Is therefore acceptable to design rock slope using the concept of rock bridge percentage? You asking me, I would say no. Others may say yes. But remember, there are some fundamental problems with Jennings equations, and we need to accept that. So we're proposing something different, and we're going to see it's not something easier. But if we're going to see the clear message, it doesn't mean because it's difficult that we shouldn't use it. Our approach is different. So we take kind of a step back and we look at the problem more in an holistic way. So what are the parameters really control? Damage. We're not talking about rock bridge percentage anymore. We talk about damage and potential for failure. You're going to have the interrock strength, the loading condition, what is direction and magnitude, the rock mass connectivity, and we're going to see the definition of it, and rock mass interlocking, which are very different. You can have a fully connected rock mass, but the blocks don't move depending on the loading direction. If the blocks don't move, the stress will have to grow basically through the interrock, and that's what can actually break. So we need to look in terms of the rock mass potential is transformed from a potentially kinematically control problem maybe to stress control problem. So we try to look at the mechanism, not just strength itself. But to determine the rock mass potential, rock bridge potential as we call it, you need to look at these parameters. And they're not easily to measure. And some of them, like connectivity, interlocking, basically fall under basically the field of probability. You don't have one connectivity, you have a potential connectivity because, as I say, you don't know what's behind the rock face. These are the definition. You can read more about this in the paper that I reference at the end of the presentation. I'm going to show you the references. But you have a two-dimensional connectivity index, NCI 2D, or a three-dimensional connectivity index, NCI 3D. And you can see the formulation for NCI 2D includes parameters you can actually map in the field. The P21 is the total fracture area, total fracture length, sorry, divided by area. P20 is the total number of fractures divided by area. I20 is the number of intersection by area. But you can see that the number of intersection has to be scaled to account for the shape effects. What is the window that you're mapping? Is it equidimensional window or is it not equidimensional? And this idea comes from, you're going to see the empirical behavior of pillars. Slender pillar or wider pillar with a ratio different behave differently. So we need to account for that. And you can technically map P21, P20, and I20 in the field if you have an image with photogrammetry. In 3D, it's more complicated because in 3D, now you're dealing with a P32, total fracture area by volume, P30, number of fractures by volume. The I31 is the actual intersection, linear intersection between fractures, and the I30 is the number of intersections. All these parameters can only be generated using discrete fracture network models. But because you're talking about discrete fracture network models, now you're dealing with probability. You have multiple realization, so don't expect one single parameter. So it's not an easy concept, I understand that. But why we keep believing that rock engineering should always be seeking easy and fast methods? We can't basically fool ourselves by saying everything has to be fast, everything has to be easy. But by doing so, you use empirical methods, and not necessarily those empirical methods are actually correct. Thinking actually in terms of quantum mechanics, again, quantum mechanics is not easy. But that's what actually needed to have basically computers, semiconductor, and so on. So we shouldn't basically imagine if someone 100 years ago said, it's too difficult, we're not going to pursue it, we're going to do something easy. We would not have what we have today. Here, an application of NCI. This is the two-dimensional version of NCI, coupled with a different geological strength index table that you may actually be familiar with. So integrated NCI with GSI. A couple of things to say. This boundary between blocky massive should not be interpreted as kind of a clear-cut boundaries. An NCI of 4 may be the boundary between massive and blocky, might actually be even 5. So we have to be flexible again with this boundary. We are kind of too strict when we build these tables. This table is different from the original GSI table because we try to really follow geological trends. So you can see the number in the cells that represent the GSI. They're not the same maybe number you're familiar with because we try to avoid this kind of reversibility problem of GSI itself. You can read again more in the paper how actually this table was created. But what you can see here with NCI is that if I have a rock mass defined as a GSI of 65 plus or minus 5, and I look at the behavior of pillars in this case, the pillars behave differently. Slender pillar with a ratio 1 or with a ratio 2. The NCI of those pillars is different, hence the different strength. So the potential is different, rock mass potential for those pillars. And this is really where we basically now look at rock bridge potential. And to do so, we have to look at the NCI after failure, this NCI RB, and the NCI before failure. What is the relationship between the two? And again, we are not here to look at the actual rock bridge potential. The importance is not looking how much rock bridge potential really I have. And definitely we don't transform that as a percentage. It's more to understand like, if I have a very high NCI RB, it means that I am really destroyed into rock. So I have a stress-driven problem. I need to break through mostly into rock. It's not about sliding on the joints. If my NCI RB is actually small, that means that the failure is controlled by structural control problems. So when you look at this one for now for some synthetic rock mass model, these are synthetic rock mass model in shear, you also appreciate another one, very important aspect. When you look at NCI, yeah, you can map it in an outcrop, but then when you do the simulation, you have to look at the NCI for the actual failure zone, because you can have a very big outcrop, but only one small portion is actually involved with the failure. You can see here the parts highlighted in yellow. That's the one you use to calculate your NCI. And what you can see here, you actually have 4 models they have not much difference in terms of NCI. I mean, the NCI is between 4, maybe 5 or 6. It actually looks like a big number difference, but it actually means they are massive to borderline blocky. They're not really on the very blocky side, none of these. It's actually the same rock mass. These models were created for a particular actually slope for a mine. The difference is the orientation of the joints and how they get together when you actually try to simulate the failure in shear. These are synthetic shear models. Some models give you more damage, other less damage. C1 almost doesn't have any damage whatsoever. So when you then group them together, you can actually switch, and you can see that you have this kind of behavior of the rock bridge that kind of linked to the actually rock mass behavior that was defined by Kaiser in 2018, this kind of matrix of rock mass behavior. Again, don't interpret these lines, the white lines, as fixed, okay? Each problem may be different, so you may actually be open to have some small variation in the way actually those lines are actually placed. They've been placed here just to represent globally what is the difference between a stress-driven problem or structurally controlled problem, and the relationship between the NCI before and after failure. So if I have a simulation, basically tells me that I have, let's say, an NCI of 10, and my NCI-RB is barely 0.5, then I'm going to be in this M31 category, which is basically structurally controlled. But if I'm basically a very low NCI, and I just generate stress-driven fractures, I'm going to be in M12 or M13, which is a stress-driven failure. So you can actually look at where you are. If you're basically between the red, the yellow, and this kind of darker green, that's the transition. You still have a percentage of stress-driven. Once you're in this structural control failure, your stress-driven failure is 0. Everything basically happens because of the discontinuities. And if I look back at the model now we showed you before, so let's assume some interrock properties, some joint properties. We don't know what they are because, well, we cannot really travel to that location. But also, even if you could travel to the location, what is the property of those joints at the scale of the monolith? So you can't tell that. Interrock will be variable as well. So let's do a simulation with some assumed properties, and we try to see what happens. And we don't say this is reality, but we can say we have an NCI before failure and NCI after failure. You can see this red line represents where the fracture is basically happening. So initially the NCI was about 4. My NCI after failure is 1. So my rock bridge potential is somewhere here, which is between 0.2, about 0.2 rock bridge potential. So what it tells you is that even if it's a very blocky rock mass, blocky to very blocky, failure will occur through basically interrock failure and stress control failure. Don't assume because you see many fractures that everything's going to be purely structurally controlled. You need to break the interrock here to make it fail. And here we're talking about a monolith barely 25 meters high, so you know what it means. The stress is just pure gravitational stress. So what is basically really make this basically structure fail is maybe whether basically the structure may actually flip side on the side rather than actually failing purely gravitationally. So in conclusion, there is no doubt that rock bridges exist, but we cannot describe rock bridges as physical objects. Their existence and definition are conditioned to the specific rock engineering problem and failure mechanisms being considered. Rock bridges become real only when we look at them, which means after they fail. So you need to simulate failure. Continuum models will not really help you in that way because can't really simulate, maybe they simulate yielding, but you need to look at the combination between stress-driven and structurally controlled. The blocks need to be free to move in your models. So my opinion, and this is my opinion, is that rock bridge percentage is no longer acceptable to simulate rock bridge analysis, rock bridge strength. It doesn't account for failure mechanisms, it doesn't account for scale effects, it doesn't account for the actual spatial variability in terms of location of the rock bridges. So there are too many limitations, and even just relying simply on fracture intensity, whether P21 or P32 is not acceptable. P21, P32, they are not measurable. They're not measure of rock mass quality. They have the same kind of limitation of a GSI in that context. So thanks for listening to this presentation. So these are some papers. The first one is actually the paper for the Slope Stability Conference, which unfortunately I couldn't attend and present the paper at. Others are other papers that I written in the last few years. They really basically depart for the standard basically concept of rock bridge percentage. And other reference cited in this presentation. If you have any questions, we're happy to ask you questions. You can just email me at this email here. Thanks for listening.